What's up, everybody? So in the interest of being helpful and saving class time, and really because a couple people requested this in period H, let's go over some of these homework problems in depth, right? So you can skip around and focus on the one that you need. This is ultimately like the level we need to get at with creating probability models. Sometimes, right, they're easy. Sometimes it's given to us. Sometimes maybe the probabilities are simple like roulette, but sometimes we got to deal with this kind of thing. So here we go. All right, so first problem we had here. So a couple plans to have kids till they get a girl, but they agree they're not going to have more than 3 children, even if they are all boys. And we're going to assume boys and girls are equally likely, 50-50 chance of each. That's not really true. It's a little different from 50-50. You can Google that when you get bored. So question A here, we want to create a probability model for the number of children that they might have. And then B, we're going to find the expected number of children. So A and B kind of go together here. So the fact that this asks me for, like really on the exam, it might just be this part B here. But the fact that it asks me for the expected number of children. So 1, that tells me I need the expected value. And anytime I need the expected value, that means I want to create a probability model, right? So just from question B, I should know that I need to create a probability model for the number of children. And then the next thing is, because we want the expected number of children, that tells me when I create that model, the number of children are going to be my outcomes across the top. So let's do it. So we want the expected number of children. And we want their corresponding probability. So the first thing we've got to think about is what are the possible numbers of children this family could have? And it tells us they're going to have children until they get a girl, but they agree they won't have more than 3 kids, even if they're all boys. So that means, of course, right, pause the video and try it, although hopefully you've already done this homework on your own. That means this family can have 1, 2, or 3 kids. Now to figure out these probabilities, right, it's not as simple as just popping a number in, right? We have to really be patient and break down each scenario. So we have to think to ourselves here, how might this family have 1 child? Well, it tells us that they're going to have kids until they get a girl. So the only way this family can have 1 child is if it's a girl. That was the weirdest that was an overline. Who overlines things? What I meant to do is, right, the only way this family has 1 child is if it's a girl right off the bat. And that's pretty simple, right? 50% chance. That's it. Then they're done. They had kids until they had a girl. Now we got to think, all right, how is it possible that this family would have 2 children? So remember, right, they're going to have kids until they get a girl, right? But they agree they won't have more than 3 kids, even if they're all boys. So the only way this family can have 2 children is if they have a boy first and then they have a girl second. So boy first and girl. Right? It can't be like girl, then boy, because once they had the girl, they would stop. They wouldn't have a second kid. And it can't be boy and then boy, because then they would have a 3rd kid, right? They're going to keep going until they get a girl, or they'll stop if they have 3 boys. So the only way that they're going to have 2 kids is if they have a girl and then The only way they're going to have 2 kids is if they have a boy and then they have a girl again. And since they're equally likely, this is just 0.5 times 0.5 or 0.25. So this is really similar to the darts example that we did in class. For the last spot here, remember these probabilities also always have to sum to 1. So this has to be 0.25, right? Because otherwise these wouldn't add up to 1. So one way to get this is just by doing 1 minus 0.5 minus the 0.25. On a side note, even if these probabilities were wrong, but if they sum to 1, like we could potentially get partially correct on the AP exam. So if I weren't sure how to figure all these out, even if I took a guess, as long as they sum to 1 and then I correctly found expected value, right, I could get some point. Now, hopefully we don't have to make up numbers and guess, but just something to think about. Now back to this 0.25, right? We could sum to subtract from 1 to figure this out. But let's consider how would it be possible that this family could have 3 kids? There's 2 ways that could happen, right? It could be a boy, and then a girl, which is going to be boy and girl. which is 0.125. So a common mistake I see students make is they just put 0.125 here, but we have to know that that's incorrect, because if this purple number were 0.125, the purple plus red plus green would not give us 1. So where does the 0.25 come from? Well, this family could have boy, boy, girl, or if their 3 kids are boy, 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 so boy and boy and boy, which gives us another 0.125, right? They're still going to stop, because remember up here, they're not going to have more than 3 kids, even if they're all boys. So whether it's boy, boy, girl, or boy, 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 right? Either way, they're stopping after 3 kids. And so here, if we then add this 0.125 for boy, boy, girl, plus this 0.125 for boy, 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 those added together give us that 0.25. So that's how we create that model, really similar to our darts. From there, I won't even do this for all these problems. I know you guys know how to find expected value, right? So the expected number of children, 1 times 0.5 plus 2 times 0.25 plus 3 times 0.25 gives us what? 0.5 plus 0.5 plus 0.75, which gives us 1.75. Now, of course, I know a family can't have 1.75 children, but remember, the expected value represents the average. Now, this probably isn't realistic, but theoretically, if families were to keep having kids under these same rules, under the same rule that they're going to have kids until they have a girl, or they'll stop even if they have 3 boys, if that situation were to occur over and over and over again, sometimes a family would have 1 kid, girl right off the bat. Sometimes a family would have 2 kids, boy then girl. Sometimes a family would have 3 kids, but if a bunch of families were doing this over and over and over again, on average, families would have 1.75 children given these conditions. So there we go. Now, if we jump up to C, for C, we're looking at the expected number of boys they're going to have. So now we're going to base it on this same probability model that we have here, but I'm sorry. We're going to base it on the same ideas that are in this probability model, but we're going to need a new probability model now looking at the number of boys. So let's do that. Kind of weird that I took that screenshot with part of my face in it, but hopefully, oh, there it is, weird. So for part C, the expected number of boys, now we want a new model with the numbers of boys across the top and their corresponding probabilities. So let's look at what we got going on here. Well, in green, how many boys is that? 0 boys, right? The only way we have 0 boys is if it's a girl right off the bat. So that's that 0.5 probability. In red, that's not 2 boys. How many boys is that? That's 1 boy, right? So this probability of 0.25, the only way we have 1 boy is if it's a boy first and then a girl second. Then here now we have to consider these 2 scenarios. So if we look in this spot in orange, here's how we could have 2 boys. So to have 2 boys, we would have boy, boy, girl, which is this 0.125 in the yellow box. And lastly, we could also possibly have in black here 3 boys, which would mean we have to have boy, 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 which is another 0.125. From there, to get the expected value, right, just multiply each outcome times its probability and add, and that will then give us the expected number of boys. So similar to what we saw with the darts today, a couple takeaways. For what's going to go along the top here as our outcomes, number of children and number of boys, it's based on the wording in the question, right? Expected number of children versus expected number of boys. And the second thing is you really got to be patient. You got to break down each scenario. You can't just expect to pop all these probabilities in 1 second or 2 seconds or even 3 seconds, right? You got to think, how could a family have 0 boys? All right, that's a girl right off the bat. How could a family have 1 boy? All right, that means that a boy first and a girl second because they're going to stop after every girl, right? You got to go through all that. Be patient, break it down piece by piece. The last thing I'll say about this one is you could model this if it helps you with a tree diagram, right? So there could be a boy on the first kid, girl on the second kid. Now, if they have a girl, they're done. If they have a boy, they're going to have a second kid. Could be a boy or a girl. If the second kid's a girl, right, they're done. If they have a boy, then they're going to have a third kid. Now, that could be a boy or a girl. In this case, either way, they're done, because if they have 3 boys in a row, they're done. And if they have a girl, they're done. So we could then use this tree diagram if we wanted to model this scenario, right? This would be 3 boys, which is going to be 0.125. This would be that boy, boy, girl, 2 boys and a girl, 0.125. By the way, 0.125, because we're multiplying across the branches. This here would be boy, then girl. So 1 boy or 2 kids, right? This is going to be 0.25, right? 0.5 times 0.5 along these branches. And then this right here is just 1 kid, no boys, 1 girl right off the bat, 0.5. So if it helps, you can model this with a tree diagram, and you could have done the same with the darts today as well. All right, next up. Okay, so play 2 games against the same opponent. Probability we win the first game is 0.4. And if we win the first game, probability we win the second game is 0.2. If we lose the first game, probability that we win the second game is 0.3. Are the 2 games independent? No, definitely not. Because the result of that first game, who cares if I spaced out my words, changes the probability of winning the second time, right? If I win the first game, I have a 20% chance of winning the second game. If I lose the first game, I have a 30% chance of winning the second game. So what happened on that first game is changing the probability I win the second time around, right? So these are very clearly related, right? What happens the first time is related to the chance, or what happens to the chance I win, or what happens the second game. So parts B and C was probability we lose both games, win both games. So we could just do these with words and lines and stuff, right? So B, we could do lose and lose. There's like a lot. And then for C, right, we could do win and win. But there's a lot to keep track of here, right? Like the probability I win the first game is 0.4. So the probability I win the first game is 0.4, which means the probability I lose the first game is 0.6. If I lose the first game, the probability that I win the second is 0.3, which means the probability I lose the second is 0.7. If I win the first game, the probability I win the second is 0.2. All right, so that's how I could do B and C. But that's a lot of information to keep track of, right? And I said that quickly. So for me, if I'm doing this problem, because we have conditional probabilities here, right? We're given some conditional probabilities. By that I mean, so like this 0.2, this is the probability we win the second game given we win the first game. And then in purple, this is the probability we win the second game given I lose the first game. So the fact that I'm given changing probabilities, I'm given conditional probabilities, to me, that suggests a tree diagram might be a good option. So here, this first set of branches just represents our first game. We could win or lose. The probability we win the first game is 0.4, which means the probability we lose is 0.6. Now, this next set of branches in green, this just represents what happens on our second game. So again, we could win or lose. So for me, I just like this visual to help keep track of all these numbers. If I win the first game, the probability I win the second is 0.2. So if I win the first game, the probability I win the second is 0.2, which means the probability I lose the second is 0.8. If I lose the first game, the probability I win the second is 0.3. So if I lose the first game, the probability I win the second is 0.3, which makes this 0.7. So I like this tree diagram to map all these out. So this is win, win, that's 0.08. This is win, lose, that's 0.32. Here we have lose, then win, which is 0.18. And then we have lose, lose, which is 0.42. Again, to get these numbers, right, I'm multiplying across the branches, right? Like lose, lose is 0.7 times 0.6. Lose, win is 0.6 times 0.3 to give me 0.18. And then, so for me, I like the tree diagram because I'm a visual person. And then probability we lose both games, question B, that's right here. Probability we win both games, question C, that's right here. Again, the reason that or the thing that made me think a tree diagram might be helpful was the fact that the chance I won the second game changed based on what happened to the first game. So I knew there were going to be, I'm pointing to the screen, you can't see me. I knew there were going to be different sets of branches because the probability I win the second game changed based on what happened the first time, right? I was given conditional probabilities. So that gets us into A, B, and C. So we want in D and E, we want the expected number of games you win and the same in the standard deviation. So we want to create our probability model. So the number of games we win and their corresponding probabilities. Well, if we use our tree diagram, this shouldn't be too bad. Well, that wasn't supposed to happen. I don't know that that was any neater. If we look in the blue situation here, what are the possible numbers of games we win? Well, we could win 2 games, and the probability that happens is 0.08. Or, well, this color looks cool. We could win 0 games, we could lose both of them, and the probability that happens is 0.42. Or we could win 1 game, which could be win then lose, or lose then win, and when we add those, we get 0.5. I feel pretty confident this model is correct because these 3 probabilities, I always want to check and make sure they equal 1. They do, right? 42%, 92%, 100%. Yeah, so there's our probability model. And again, we could do this without the tree, but that can be tricky because there's a lot to think about, right? This would have to be win and win. This would be lose and lose. This would be win and lose or lose and win. But then you got to keep track of all those different probabilities that are changing in your head. So I really, really think the tree diagram is the way to go for this one. From there, to get expected value, right? 2 times 0.8, 1 times 0.5, 0 times 0.42, and add them up. But for this one, since we want the standard deviation, I'm doing this in my calculator. So I'm just popping these in L1. Like I haven't even talked to you about how to find the standard deviation by hand. I'm never gonna. Why would we do that? Just use the calculator. Pop these in L2. Then I'm gonna go stat calc. I could obviously be doing this on the screen, but hey, you do it. Pay attention or something. 1 var stat. Then when it pops up, my list, those are my outcomes. So that's L1 or wherever I typed the numbers of games won. And my frequency list, my probabilities here represent how frequently each thing happened. So they don't have to be in L1 and L2, just in general. L1 is always, or well, I'm sorry, the list is always your outcomes, which in this case is the number of games won. And the frequency list, those are our probabilities, which I entered in L2. Then I'm going to press calculate. And it's going to give me the expected value, which is the mean, right? That's my expected value, whatever it says on the calculator. And sigma is my standard deviation, right? So I just pull those off the screen. Lastly, if you got an older model and it just pops up and says 1 var stat on your screen, right? You have to type L1 comma L2, or not necessarily those things, but just wherever your outcome list is, comma, wherever your probabilities are. Tearing through some homework. All right. I'm starting to like wonder if I press record. I really hope I did. It would be pretty bad if I didn't. Last one. Got 10 batteries, 3 are dead. We're going to pick 2 at random. Seems like a bad way to keep our batteries just all mixed together in a bag. Why am I saving dead batteries? Seems real dumb. Let's pretend this question isn't even there because we shouldn't need that. Once we see this, what's the expected number of good ones we get? Again, that expected value, that means we have to create our table. And what's going to go across the top? The number of good ones, the ones that work. So the first thing we have to think about here is I'm going to choose 2 batteries at random. how many good ones could I get? I guess they both could be good. Or they both could be dead and I get no good ones. Or I get one good one. If I'm doing this question, I'm starting with these kind of outside probabilities, the 0 and the 2. So to get 0 good batteries, that means the first one's not good or it's dead, and the second one's not good or it's dead. What a tough life a battery is. You're either working or you're dead. That's a Dimitri Martin joke. He's a comedian. Google it. I stole it. You're not even laughing. All right. So the probability the first one's dead and the second one's dead, that's the only way we get 0 good batteries. Like I'm doing this quick, right? But I don't want to have a 9-hour YouTube video. But like that's a lot to think about, right? You got to take a step back and think, how can I have 0 good batteries? All right, I take the first one is dead. I take the second one's dead. All right, now I know that I have 10 batteries and 3 are dead. So the probability the first one's dead is 3 out of 10 times, but like you're not going to take out a battery and then put it back in. Then you would never have 2 batteries in your hand. So we have to recognize that this must be done without replacement. So the probability the second one's dead is now 2 out of 9, right? I took out 1 dead one, so there's only 2 left. And that gives me 6 out of 90 or 0.067. Similarly, over here, to get 2 good batteries, that means I took the first one out and it was good, it worked. And then I took the second one out and it was good or it worked. Well, there were 10 batteries and out of those 10, 3 were dead. So that means 7 of them were good times, well, I took a good one out. So now there's 6 good ones out of 9, which gives me 42 out of 90, which is 0.467. Now, the reason I said I would do those 2 first is to then find the middle number. I would just subtract 0.067 and 0.467 from 1 and get that number. So now I know this middle value is 0.466. And again, from there to get the expected number of good ones, I think we're good with that. But I guess since this is the last problem, I'll write it down. So the expected number of good batteries is going to be 0 times 0.067 plus 1 times 0.466 plus 2 times 0.467. It's not going to be 0, 1, or 2, right? Again, this represents the average. If I were to theoretically do this over and over and over again, sometimes I'd get no good batteries. Sometimes I'd get 1 good battery. Sometimes I'd get 2 good batteries. This represents, if I were to continually do this over and over and over and over and over again, this represents on average how many good batteries would I expect to get. Lastly, finish up. Just to be clear in practice, where's this come from? Well, to get 1 good battery, the first one's good and the second one's dead. Well, that doesn't even look anything remotely close to dead. We'll do this. So the first one's good is 7 out of 10 times the second one's dead. There's still all 3 dead ones, but now there's only 9 batteries. So that gives me 21 out of 90, which is 0.233. But that's not the only way I could have 1 good battery. So I'm going to have to add, or the first one's dead and the second one's good. 3 dead out of 10 times, I still have all 7 good ones in there. I haven't touched those out of 9, which is also 0.233. And if I were to add these, that's how we directly calculate that 0.466 right there if we didn't subtract from 1. Homework done. See, that was like easy, right? No, it wasn't. You got to be patient. You got to practice. Take your time. Do stuff.